So module 3, polynomials, polynomial functions, if you will. We'll just say polynomials. Polynomials. Big ideas with this. We have polynomial functions and equations, etc. Functions defined by equations, however you want to look at it. But I guess one thing to notice is, first off, it's an extension of what we've already been working on. You had linear functions and quadratic functions in the last module. Say we took f of x equals 3x minus 5 or something like that. That's a linear function. It has just x to the 1 power, and then g of x equals, say, 4x squared plus 7x minus 2 or something, whatever. If you have an x to the 2, we call that quadratic, and we saw some different properties about those and mentioned some things about it. Linear ones, we had this idea that it made a straight line, and hence the name, and a straight line pattern because of the predictability of the consistency of the outputs, when you're plugging in numbers. And then we saw the graph of these quadratics tend to have two pieces to it, there's a down and an up, or an up and a down. And we know all the other things we mentioned about those. And so then, there was patterns in the outputs where the slope seemed to be ever increasing, or, whatever. Okay, so polynomials is taking this idea of saying, well, say we included those and expanded the idea. X to the 1, x to the 2, keep on going. Say we have more functions of x. I could have maybe just call them all f of x, so we don't have to keep up coming up with names, x to the 3, and f of x equals x to the 4, and la la la, x to the 5. If we keep on getting more and more complicated with these, x to some greater power, as far as we want to go with that, dot, 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 keep on going with those, x to the whatever power. These are all what we call polynomial functions, where there's no other kinds of complications. We're not dividing out weird x's or adding any other weird complications to it, but we're just saying get as complicated as you want with powers of x, And so only other thing to mention about that is, one thing that we haven't given much attention is, well, we can even go below x to the 1, of course, with polynomials. We can say, well, even down to if I just had a constant function of like f of x equaled 7 or something, and there was no x's, well, we say that's essentially us saying like, well, this is like x to the 0, because there's none of them. And so we're going to go ahead and loop that one into the world of polynomials as well. So I guess that's what polynomials are, is it's all these functions that are just, combinations of numbers, constant numbers timesing with different powers of x's, and without any other weird complications involved with square roots. Should we know about them? Where will we be focusing? What is our big idea here? And so a couple of things. For one, notice some patterns in what we've seen so far with linear functions. We have x to the 1 or whatever. We've seen those. I'll go ahead and put x to the 1. Those, again, we noticed a straight line pattern. The consistency of the outputs, has a very consistent pattern in the outputs compared to the inputs, and whatever. That's where we get slope ideas from. It has essentially just kind of one direction that a line will ever go, or I guess you could say in one dimension, because it's going both forward and backward, but whatever. However you want to say that, it's going one way. And so then x to the 2, we notice that it has kind of two ways that it goes. And these are, of course, very loosely defined terms. We can define them more, how do you say that specifically if we need to, but for now, I think it's good. We have x to the 2 has kind of two pieces to it. There's a down and an up, not to say that it's like an absolute value function where it's just a straight down, a straight up thing or anything, it's curvy and it keeps on bending with an ever increasing slope, but there's kind of two pieces to it, a down piece and an up piece, a decrease and an increase, if you will. And then if we have an x to the 3, something that we haven't noticed about these before, something we haven't touched on, is an x to the 3 function has 3 pieces to it, Not to say that that's obvious. It's not obvious. Feel free to graph a few of these, But if we're talking just big idea, we notice that x to the 3 has 3 pieces to it in the graph of the function. If we're looking at the outputs and the patterns in the outputs, I keep on plugging in numbers, then x to the 3 functions seem to be going uphill for a while. Then at some point they're going as uphill as they're gonna, then they go downhill where the outputs actually start to get to be smaller for a while for some reason, which is crazy because you're thinking, well, why would the output numbers, if I'm thinking input and output, if I'm plugging in like 1 and 2 and 3 and 4 and 5 for my x's, then why are my output in, out? Why are my outputs getting bigger and bigger for a while? But then they're like 10 and then 100 and then 1,000. And then after a while, and then at some point, why are they getting smaller again, going back to 100, and then back to 10, why would that happen? Well, it's stuff we can talk about. Anyway, then they go back up again. I guess the idea with these sometimes is like, well, if you have something to the third power, a negative to the third power, of course, is a negative, and a positive to the third power is positive. And so that would be maybe part of the idea behind like, why do we see a decrease sometimes is because, well, we're seeing negative things go on. But then again, that one might describe the left-hand tail better than it does the middle. So there's a little bit more mystery involved in that. Still, let me undo that thing right there. Okay, nonetheless, where I wanted to go with this stuff here is not so much talking all about that, but let's talk about the pieces here that we're seeing. Something that's worth noting, we have x to the 1 piece, x to the 2 has 2 pieces, x to the 3 has 3 pieces, and that pattern keeps on continuing. It's related to some kind of a fundamental theorem of something, I believe. But what we got is, let's not worry about proving theorems. We have, it's this 4 pieces thing, and then you can bet x to the 5 will have 5 pieces to it. 1, 2, 3, 4, 5, and up, down, up, down, up. And of course, it could be the other way. It could be down, up, down, up, down, depending on this behavior. We're talking long run behavior, depending on the lead term, this and that. Whatever, though, we got 5 pieces to an x to the 5 complicated function, And so this is interesting. We notice these are the behaviors of polynomial functions. Notice one thing about them is that they are these polynomial functions, because they don't have any other weird complications to them, but they're just powers of x. Well, they don't have any brokenness in them. They're continuous functions. So if I were to look at the graph on like an x and y Cartesian grid, well, all we see is a bunch of wiggle around, and then they're done wiggling for a while, and then they go up forever or down forever after that, after however many pieces they have, even if it's just 2 pieces, like we said, with the quadratic. Well, what they don't have is any brokenness. That starts showing up later on with more complicated functions. We have, it's not going to ever get to the place where you're like, well, the function goes down here and then it picks up again right there or something like that. There's no brokenness where it's got, 2 different pieces to it. We call those discontinuities. These are all very continuous functions, and all we see in them is up and down wiggles, and that's all they're characterized by. And so I guess the big picture, besides noticing these things that we've already noticed, is this. Well, say I had an x to the 5 function. Well, we know that that has 5 pieces to it. Well, notice how that could go. We could say wiggle up, wiggle down, up, and it means things like this. Well, if you kept on wiggling up and down, you're going to be crossing over the x-axis some number of times, not to say you would have to 5 times crossover like we did. Like you could go up, down, up, and then you only cross over it once, really. It's possible to do that. And we can talk about all that, but we'll take a generic idea here and say, well, it's possible we could cross over this x-axis as many as 5 times with a 5-degree polynomial, a degree 5 polynomial. Now, what that indicates to us, guys, is, well, these are, I guess it focuses us in on this notion about finding, well, where are these places? Where are these places where we cross the x-axis? Not just because it helps us to draw a good picture of some function, but because remember what functions are used to represent. And if we're talking applied mathematics, well, okay, if we think x and y values here, on the y values, when we are above the axis, those are positive outputs, and below the axis are negative outputs. So when we have a place where we hit the x-axis, well, that's a transition from positive outputs to negative outputs, which means, well, for one, there's only one number that's between positive and negative. That means it's 0 output, but it means it could be a very important transition point depending on what application you have in mind, or even if we're talking about just pure mathematics, there's a transition point here. If we're talking about, say you were made a function, and we don't always use polynomials for this, but say you had a function that was talking about describing the profits of some business, and you're watching them go up and up and up and up and up, and profits are really high and they're downhill now. You can see it's starting to get in a bad place. Well, it's right here when your business is really in a bad spot, where you notice that you crossed back over that break-even point, and now your profits are negative and you are making less money than you are spending, and that's what this point here, we call it an x-intercept, indicates, and so most of our energy and attention in module 3 is going to be focused on finding those points. We call them x-intercepts when they're on a graph like that. Otherwise, we call them zeros of a function. And there are, of course, times when the zeros of a function are not the same thing as an x-intercept. We might talk about that, but we'll just say, well, we'll get there in a sec. For now, we'll call them equivalent. Every time that our graph hits that x-axis is a place where our outputs are not positive upstairs and they're not negative downstairs. They are zero in between positive and negative. It is a crossover point. Could be a bad thing, crossing from positive to negative, or it could be a good thing when, say, your profits are finally turning around and you have, wham, now you have your business is at a break-even point and finally you've broken through after a few years of trying or something, and now we got positive profits here, where our revenue minus our costs or whatever is going to be positive outputs. And this again became a turning point for us, not to say it has to be about money or anything like that, but we're just talking about transitions in any setting between negatives and positives. This could be particle motion, Brownian motion, talking about left to right or whatever. If you want to go in that direction, doesn't really matter. This is a transition point from being on the left to on the right, or from positive to negative, or whatever it is. And so that's why we always look at these, what we call zeros of a function, or in the picture of a graph, we call them x-intercepts a lot of the time. Okay, that is what a lot of our module 3, like most of it, is centered around. Like, that's the whole big idea, is finding these things. So all of these skills that you'll be going over about long division and this and that, right now, they're focused on the notion of, can I find these zeros of these functions? The only other thing to mention here, guys, I guess there's a couple of things. So the only other thing to mention here, that's right now anyway, would be it is possible that you would have a function that has a zero of the function where the output is 0, say, but it is not an x-intercept, And so watch out for that. It's possible that we would ever find, and here's, I guess, what the end of the, whatever chapter 3 point something gets into, is where we get into complex maybe let's not go overboard. Check this out. Suppose for a second, let's go this way. Way better. You're gonna love it. Okay. Suppose we went this way. And I was like, say I had to figure out the square root of 9, and we're like, well, easy enough. I can figure out the square root of 9, that's 3, And we talked about this maybe in an earlier video, but maybe in a different way, because we're making a new conclusion now. Square is 3. And so if we use a radical here, that indicates the principal square root of 9 being 3. Okay. If I put my little plus and minus on it, that means it's okay to find any square root of 9. And so I'd say, okay, or you could even say it in words. If you didn't want to use symbols, if you don't like that, you can just say find any square root of 9, that would be fine. Fine. Oh, wow. But just pretend like I can write stuff. Any old square root of 9. Then we'd say, okay, square root of 9, without getting into the symbols or anything. We'd say, well, I guess that's 3. The square root of 9 is 3, and I'll do it in words. Square root of 9 is 3. Or you could even say, well, I guess the square root of 9, I could say, is -3 also. That's also a square root of 9, because for the same reason, we define a square root to be some number so that when I square it, I get 9. So we could say square root of 9, well, 3 is a square root of 9 because, we'll abbreviate because if I take 3 and I square it, I get 9. And then the same thing with -3, that is a square root of 9 because, there you go. because -3, if I square that, well, that's a negative times negative, -3 times -3, that's also 9. So they both meet the definition really well. And so it's no problem. What it means is I can picture on my number line, if I have a number line and I'm trying to picture, well, where's the square root of 9? I know where 9 is. Here's the square root of 9, it's 3. It's right there on the X line. And here's another square root of 9, is -3 on my X line, on my real number line. We could think of that as the X inputs, it's fine. But then here becomes a problem. What if we ever had to find, though, say we had to find, here, let's not section that off. We'll just kind of section it to the side. But can we find a square root of -9? This is something that maybe you've run into before. Square root of -9. Make that look like a cube. Square root of -9. That's going to be tougher because essentially it's challenging me to find some number. I'll put a question mark until we figure it out. Some number that when I square that, some number so that when I square it, I get -9. And that's problematic because if it's going to be a 9, it has to be some kind of a 3. But both of the 3's are already taken up. And so some number times itself is supposed to be -9. We're going to have problems, because 3 is surely not going to do that. And -3 doesn't do it either. And then you look on your number line, there's no other 3's. There's only +3 and -3. There's not some other kind of 3. There's not any other kind of number. We just have positives and negatives, and then 0 in the middle. So there's not going to be another 3 on this number line unless we find some new way to invent things. And so kind of like that's what we're challenged with, is if you ever have a square root, and this comes up, the reason I bring this up is because it comes up as we're solving some of these polynomial equations and dealing with the functions. Finding zeros is sometimes you'll find yourself square rooting a negative, and then you're like, well, okay, I found it, but I don't know where to draw it, because you're trying to draw a graph of this thing and it's got a number line 1, 2, 3, 1, 2, 3. And if I had to draw a square root of -9, I can't draw it there as an x-intercept, and I can't draw it there as an x-intercept because it's neither one of those 3's. It is not a real number, and so that's where we start to invent this idea about an imaginary number. And what's crazy about that is, well, where is that 3? It's got to be some kind of a 3, but where is it? It's popping off the line. It's 3 stubs that way or something, we don't know. And so this is where we invent the idea of the complex plane and stuff like that. We can get into details about it, but this is a big picture thing. So that becomes a new idea. And that's why we say that x-intercepts are not the same thing as zeros of a function, because now when we run into problems like this, it's possible for me to be dealing with a function algebraically and find a 0 of a function, but when I'm drawing its inputs and outputs, it's not one of these, because my number that I'm looking for is a square root of a negative, and it's not this 3 and it's not that 3. It's some other 3 that's not on the line, and I got to figure out where it is. And I suggest to you, it might be in a whole other plane here, popping off the page in a different direction, a different dimension, if you will. Anyway, that's plenty for now. The only other thing is we have the idea of equation and inequality solving. I'll keep this one short, but this is the only other big idea stuff here in the whole section, or in the whole module, is solving some equations with these. You know what? I think I'm mixing it up with another module, so I think I'm going to end that here. Yeah, that's good. I feel like this is pretty comprehensive. So pretend like I didn't bring up the word equation here. We'll undo it real quick. See, never happened. Okay. Anyway, that's all the big idea stuff.